Welcome to this CO₂ Design Fundamentals 4-part series. So excited that you're all here. We're going to be diving into some deep CO₂ technical piping design. I'm here with my good friend Chris Griffiths, and we're always talking about CO₂ design, learning and growing. We want to share this knowledge with you because we want to help you. We want to help you become a better designer, a better engineer out there. And all the people that I talk with around the world, they want to get better at CO₂. We know it's growing and it's getting bigger and bigger. You're getting opportunities out there to design CO₂ systems, and we want to help prepare you for that. Chris, how you doing, brother?
Doing well, Trevor. Doing well. Excited for this.
Yeah, me too.
My favorite topics, especially pipe sizing. So off we go.
Yeah, no, you're an expert at this, and this is what you do day in, day out, helping customers solve some of the toughest problems in piping designs, because they come to you to solve that problem. Like, we're running into an issue. What is it? And then you can go in and you can calculate it. And these are some of the things we're going to talk about today, getting into protect the compressors, and that's the big thing when you have improper piping, or you make a mistake or an error, or something does happen, something changes. This could really cause more energy usage. It could cause components to fail, could cause compressors to fail, and we do not want that. We want you to be super successful for this. So definitely, Chris, let's start diving into CO₂ pipe design.
Great stuff. Okay, so today, as you just summarized, go look at design tips specifically to try and protect compressors and prevent failures. So a primary purpose of pipe work is to generate a cooling effect where we want it. We circulate a refrigerant around the system. A sealed system, we don't want it escaping. But as part of that, the compressor needs to be protected to ensure it can do its job. So we're going to start off today with what I consider the top 3 tips for protecting compressors, and they all come back to oil and making sure that oil flows around the system back to the compressors if it does escape from the compressor in the first place. So number 1, and the fault we find generally occurs and people's confusion around, is suction risers. Oil will flow absolutely fine back to a compressor provided the pipes are sized appropriately horizontally with a minimal fall back to the compressor. But as we all know, how often do we actually get systems where the evaporator is above the compressor at all times? Minimal. I can't think of a single supermarket out there which has that, or retail application. So making sure we can actually get that oil back up any risers and work against gravity is key to making sure our compressors are protected. To do that, we need to make sure it actually returns oil at both full conditions, as we designed for. We need to make sure we get the full mass flow of refrigerant through the system. The oil will be entrained within that, but making sure it also returns at part load conditions, because these systems don't operate at 100% capacity for 99% of the year, or at all in a year. You may get a freak environmental condition once every 4 years, which we still have to design to, but it won't be operating at those conditions for the majority of the time. So making sure we check our designs at both full load and part load, whether that's 20%, 50%, 80%, etc., making sure that's actually designed appropriately to do so. Making sure any horizontal sections of pipe work flow down towards the compressor, and then ideally we don't get the oil escaping from the compressors in the first place. Let's make sure we've got any oil management systems there, make sure they're operating and make sure they're maintained effectively. So oil management system piping is a specialty in itself as well, which is something we do cover in the CO₂ training course in far more in depth. It's a bit too much to cover in even a 4-part series as this is, but making sure that's actually designed appropriately is, again, fundamental for what we need.
I think that was some of the biggest game-changing stuff I've seen in our 12-week design courses, where we see the designers, they take that one approach on that, the hottest day of the year of the approach. And then all of a sudden we start to go into the part load, because we know here in Canada, it gets so cold, and we don't have that mass flow like you do in the middle of the summer. And then looking at the difference and seeing the designers doing those tasks as trying and looking forward to the customer. These are our options. What is the best option? Because sometimes you can't do much about the design, but make it the best and most efficient as possible, correct?
Exactly. The ideal perfect conditions never exist, and the ideal design never exists. Particularly with pipe sizing, the actual correct size may be halfway between the 2 pipe diameters which are actually widely available. which manufacturers aren't going to manufacture a huge run of specialist pipework for such a small application generally, unless it was a very, very specific design with a budget to do so. And we have to work within budgets and constraints, and that's what makes it fun engineering rather than what do the numbers spit out? What can you do? So with this, if we do get our pipe sizes wrong, there's multiple ways. It's either going to be too large, too small generally. So if it's too small, we get insufficient mass flow through the system. We can't actually generate the amount of cooling we need to do the job. If that doesn't happen, the customer's products aren't kept cool, they can't sell them, they make no money, the system is a failure. For liquid lines, you get excessive velocities and you end up getting what we call liquid hammer. When it comes up to a valve, there's a lot of energy inside that fluid. If you try and shut the velocity down, that energy's got to go somewhere. It ends up forcing its way into the walls of the pipework, which can shake the pipes. Where's the inner walls of the pipe? If it's against bends, long radius elbows, short radius elbows, eventually over time it will fracture those and it will leak out the system. On the other hand, if the pipe diameter is too large, you get insufficient velocity, particularly concern on suction. You won't get the oil return. You'll have spent way more money than you need to in installing it. The larger the pipe, more expensive it is. And you'll also have an excessive refrigerant charge in your liquid line if you oversize that as well. Why have more liquid in the system than you actually need? Why spend the money on it? You don't need to. And then eventually, if you did have too large a liquid line, you would not actually be able to pump the system down generally because the receiver won't be large enough to accommodate it as well. So try and design with these constraints in mind with those two, and you won't go far wrong. Less common from that, we have if you have too many bends, you get excessive pressure drop. That's going to reduce the efficiency of our system. Using long radius bends should be preferred rather than short radius bends. Short radius bends will induce more of a pressure drop in the system as well. And then we go back to our installation techniques. So, for example, making sure suction pipework slopes down towards compressor, which helps with oil return. Making sure oil traps are installed on risers to make sure we can actually return the oil at part load conditions. And then also one which most people don't consider is actually having appropriate pipe insulation on the pipework, particularly with CO2, because we operate below the dew point on both suction and liquid. We need to make sure those pipes are well insulated. At low temperature conditions, we're talking deep freezing, you should have at least an inch wall thickness at minimum, if not even larger if you can get it.
And this is something important when we talk about in that design program is when you're calculating the price for it for your customer. When we get in there, this is important because that insulation is expensive. So you got to calculate for that as long as because if you oversize it, just like we said, there's more refrigerant potentially if you don't have that insulation or the thick enough insulation and a good insulation as well, because we see lots of insulation that breaks down very quickly. So that is important for that pipe.
Definitely. So the purpose of today, because we've not got a huge amount of time in each one of these sessions, I thought we'd try and break it down into what's most key and what we find most on sites cause issues. So insufficient pipe sizing is the main one here. As I've already said, insufficient system capacity is the main issue at the end of the day. We want to make sure we can actually cool what we need to do. And if our pipes aren't large enough to carry the refrigerant, it's not going to happen. We have our excessive noise and vibration if there's too high a velocity running through it, particularly on liquid. But what I want to speak more specifically on is suction pipes and how it impacts that. So we're looking at excessive pressure drop and eventually leading to oil issues as well. So we're going to move swiftly on and we're just going to have a look at some of the actual pipe sizes themselves and what impact it can have. So for the purpose of this, we've selected a small example system here. There's a lot of numbers on here, but effectively a small dual temperature system. So we've got a freezer based around 5 kilowatts, which is 1.5 tons, I believe.
Yeah, close.
With a medium temperature side, about 14 kilowatts, which would be sort of 4 tons, 4.2 tons or so. Half-inch suction for this, and in the top we've got highlighted our DT saturated temperature in Kelvin. That's our pressure drop equivalent there. So a 1/2 inch pipe, the full load on that is 1.1 Kelvin. So that's our equivalent pressure drop there. That's a sensible pressure drop to design to for suction pipes. Between 1 and 2 Kelvin should be sort of 1.8 to 3.6 Rankine or Fahrenheit. From that, we've also selected our compressors. We've used a bits of software here. And on the right-hand side, you can see our medium temperature stage. We've got an evaporator capacity of 14.08 kilowatts, so just above what we need. Absolutely perfect. And you'll see we have a power input of 12.13. We have a discharge temperature there of 125 Celsius, fairly warm. But the more important thing is we're going to contrast this with the same system if we used 3/8 pipe. You can already see in the table at the top, directly above that 1.1 K saturated pressure drop, we've got 5.4. That is a huge increase and is well outside of design considerations that you'd normally use when selecting pipework. But for the purpose of today, let's go with it. So before we move on, we've got a coefficient of performance of 1.43. If we did swap, or if we had installed 3/8 pipework as a suction, which with CO₂, for those who aren't familiar with CO₂, we can get away with generally a much, much smaller diameter pipework for the same duties we would have on HFC and even HFO systems as well. It's drastically smaller. It's no longer big pipe, little pipe. It's little pipe and little pipe. And particularly when they're both insulated as well, it gets even more confusing to make sure which ones are piped up the correct way around on site. So something to consider. So on here, if we rerun those numbers again with our much, much lower or much more increased pressure drop, we'll see with the exact same compressor, same conditions, our evaporator capacity has actually dropped from 14 down to 12. Well, now, when we need it the most, we haven't actually got enough to cool everything we need in our shop, in our store. Our power input has also increased from 12.13 to 12.47, and our discharge temperature has increased by 10 degrees. As our discharge temperatures get even hotter, the quality of our oil in our system decreases. It gets eventually it'll break down. It won't actually lubricate the compressor as it should do, and we're going to run into even more issues. And then the nice, easy number to recognize when systems aren't performing very well is our COP, has decreased from 1.43 to 1.28. So not only are we no longer actually achieving targets we set out to achieve with cooling this system, we've also used more electricity to do so, to even try and attempt to get there, purely just from dropping the pipe size. And for those who are involved in project management and costing projects, the difference in price between 3/8 copper and 1/2 inch copper isn't drastic. Even using K65 iron alloy, it's not worthwhile trying to penny pinch and skimp on this bit. Install the pipework as it should be. So how do we actually check those pipe sizes are correct? So we had that little table on the top of the last two slides. That's done in Danfoss Cool Selector, and that's what I'll be showing on the next several slides. So just to set the basis for this, we're going to look at an example system which has a cold room evaporator and 2 display cabinets connected to it. It's only a small condensing unit. Say this may be a small retailer or convenience store. So we're going to have our pipe sizing selection software. We're going to check compressors, manufacturer's data sheets, and we're going to have an example of a couple of selections we've already made here. So the top right-hand side, we've got an example evaporator selection. It's a Kelvin evaporator. We've got 4.2 kilowatts, and then we've got our display cabinets on the bottom right. We've got a 12-foot and a 6-foot cabinet there. 12-foot is 6.2 kilowatts, and our 6-foot is 3.1. Those are all the numbers we need now to be able to start plugging it into our system. So with pipe work, we need to do some sort of schematic to know where the pipes are actually going. So we've got our example system here, our 2 display cabinets. I've just included a little bit of information on that in terms of capacities, our evaporating temperatures, and then a rough dimension on how they all fit together. Normally, we'd also label these up to show the distances between them, show any valves, fixtures coming off them as well. We're trying to keep this simplified for today. Let's say we have an issue where the entire system is not performing as it should be. And we think, well, all 3 fixtures on the same system, the same network, aren't performing correctly. Is it something to do with pipework? Well, let's have a look. If it's affecting all 3 of them, the fault is probably going to be between the first evaporator you get to from the condensing unit back to that point. So what we can do is analyze this section of pipework highlighted in red. What we'll do is break that section into various parts. We'll use Danfoss Cool Selector here. There are other softwares out there, for example, White Rose MicroPipe, which would do this much quicker. But Danfoss is free for people to use online, and it's fairly intuitive as well. So we'll break this red dotted section into its constituent components. So we'll have our directional flow, whether it's horizontal, going upwards or downwards, and then the type of bend and how they fit together. So what I've modeled here is using 1/2-inch pipe. We would have a total pressure drop highlighted in the right-hand box towards the bottom of 1.1 Kelvin. Similar as we showed earlier on in the presentation, that's a sensible pressure drop to work with. So if we're evaporating at -6 Celsius, we'd have a saturated suction temperature, what our compressors would see, at -7.1. And all our selections for our compressors would be based around that. What if this is incorrect though? What if this was actually installed as 3/8? We have a pressure drop there instead of 5.2 Kelvin. Similar to what we showed earlier, that's a huge drop, but we can see now we have a bit more information on each section of pipework here. When we're selecting pipework, we generally try and base it around 2 things, the overall pressure drop and also ensuring our velocity is correct throughout. Velocity will change depending on the refrigerant type and what element of the system it's in. For suction pipework, a rule of thumb typically for HFC pipework would be between 8 meters a second and 18. For CO2, you can generally go a bit lower, probably about 5 the lowest. You can go lower, but I'd be hesitant to do so without checking it in some more detail first. But we can see here, if I can engage the laser pointer for this one, our velocities through this suction line are quite high, and up our riser here as well, we've got 15.8 meters a second. That's fairly high, not excessively high for a HFC system, but CO2 will carry oil very, very well. It doesn't particularly need the velocity that you'd normally have on other refrigerants, purely because it's a very useful gas. It's very dense gas in comparison, and it carries heat around very well. Hence why we have smaller pipework. So we'll have a look at this. For a velocity for a riser, I'd say that's okay. Then we look at the overall pressure drop through the rest of it, and we've got 0.6 Kelvin there just in our riser. It's a fairly high pressure drop, but it's only a small section. It's a 3-meter riser, or 10 foot. That's okay. What about the rest of it though? Well, our straight length of pipe immediately after, it's 10 meters, 30 feet. We've got a pressure drop of 2.2 Kelvin, nearly 5 Fahrenheit there alone. That's a huge drop. In reality, if I was concerned that the velocity would need to be that high, I would say you'd step all the other pipe sizes up by 1 size, up to 1/2 inch, and leave the riser at 3/8. But we can probably get away with stepping that up as well. Realistically, we want to be sizing it for full load conditions. What we could do afterwards, if we select it all as 1/2 inch, is rerun the same pipe sizes, but with reduced duty here. So instead of 14 kilowatts or 4 tons, we'd drop it down to 2 tons or 7 kilowatts or even lower. On our network, what if the single cabinet is operating? Because the other cabinet and the evaporator have satisfied themselves to temperature and they shut off. Well, you've only got probably a quarter of the duty and a quarter of the mass flow through the system, but it still has to go through the same riser and return all the oil that it needs to the compressor.
Yeah.
What if it's too large? Sorry, Trevor, go ahead.
That's super important, because I've seen it time and time again where oil issues happening because of that, and having that high pressure drop in, if it's not checked and not verified. And I know we're going through the Danfoss software, but in micropipe, I've seen it time and time again where the students start to use micropipe, and it's a middle pipe in the middle of the piping train or network. You can go and you save all those piping, so you don't have to go through each step, which was really cool about micropipe, and it gives you that option to change those. So I really enjoy that software.
It's a game changer, particularly if you have a project with, we've got a very easy one here. We've got, for example, 2 cabinets and an evaporator. Larger stores, you may have 100 fixtures on one system. Dual temperature as well. And then they decide to move halfway across the store, or change it from 6 cabinets there to 4 cabinets and move 2 onto another stub, rather than having to rerun the entire network again, or even simplifying it into sections. You can actually model it exactly as it needs to be. Your index run may change, so your worst case pressure drop might move from halfway across the store to the other half, and then it's still going to have an impact on your compressors. So it should help considerably. Just seen a question come in. Why is there no trap on the suction riser? Purely because I couldn't fit all of it onto the PowerPoint slide. I've cheated a little bit on this one, I'll be frank there. But yes, you would model the additional 2 90-degree bends onto the system. Or you could have 2 45-degree bends and a 90 to drop it down before it rises up again. Or pre-manufactured P-trap, U-trap style thing. So, for example, on here, if we look at it being too large now, our pressure dropped. We have no pressure drop at all there. Great, our system's going to perform very efficiently. However, the velocity here, 3.84, says to me that it is going to not return oil very well. And this is at peak conditions. So if we drop that capacity down to 50% or even 30%, there's not a chance that oil is going to return up that riser. At that point, we could introduce a double riser and have a second smaller riser coming off the top of it to return at part load conditions. For the sake of 3 fixtures, is that really worth it? Particularly on CO₂, I've designed a lot of CO₂ installations. I don't think I've ever had to use a double riser. It just doesn't happen in retail unless you have a huge number of fixtures only returning up a single point. And at which point I would tend to split those into multiple headers on top of various cases, just to simplify it, reduce the risk, eliminate the risk first rather than trying to mitigate it. That should always be the idea.
And that's why you're one of the best. Love it.
That's it. Yeah, we'll go with that. Yeah. Just before we move on as well, vertical height from the evaporator to compressor is more than 4 meters. Is a U-trap sufficient or must use double riser? Neither. So put a U-trap in anyway, because it's important for that oil to be able to build up at part load conditions until the pressure behind it is enough to force it up the trap. And also you don't want it then running backwards, potentially back into your evaporators. We've managed to get it up out of the evaporators to the base of the riser anyway. We don't want to undo any work that the system's already done to do that. So we end up putting that trap in. In terms of a maximum height on it, it's good practice to put an additional a trap in. Generally, I always did 6 meters. Some people think that's probably slightly too much. That's 30 feet. CO₂ is very good at transporting oil, though. That's the important thing to consider there. I know for HFO designed systems, a similar system to this, I would be probably installing a double riser, because to ensure that velocity can return oil at part load conditions. It's good practice too. But again, model it, make sure you're not getting an excessive pressure drop whilst still maintaining a decent velocity on the system.
I love that.
So with our example system, say it was installed and we found actually those pipe sizes were 3/8 between all the evaporators back to our condensing unit. Our suction pressures lower than we would expect it to be, and we've got 24 bar, 360 psi, we can confirm to ourselves, we can even run it through the compressor software, that is outside of our operating envelope and we're not going to get the coolant that we need. And the solution for that, nice and simply, increase pipe size diameter. Much cheaper to do this at the design stage and run the numbers rather than install it, wait for a fault to happen, and go back and repair it then. You're talking maybe an hour, 2 hours of your time as a designer to change it and verify it before it is installed, versus a day, 2 days of labor on site, all the materials associated with it, downtime for the customer. Yeah, do your due diligence first rather than waiting for it to be installed and it go wrong. So very quickly, just have a quick look on oil traps and risers. If there was a fault with these, if you go to the site and you find the system showing signs of low oil, but no oil leaks are visible, what could it be? Is the oil getting trapped in the riser? Is it getting trapped in the evaporators? So try and go through logically, find out where it would be stuck, check your velocities for each riser. You can model that in software fairly quickly. If you know what duty the system needs to be based on manufacturer's data sheets, or even looking at the condensing unit, you can model it fairly quickly. You don't have to go in depth on every single component. You'd just be looking at the vertical component of that riser. And if you do need to install a double riser, that is the sort of configuration you'd be using. So you'd be looking at part load, you'd base it on that smaller riser, and full load based on the larger one. You should really, if you can model it, base the flow on both parts of the riser combined. That's going to be very difficult to do in a piece of software like Danfoss. If it's returning at the main riser and that's what it's been sized for, great. It's not going to suffer by having the smaller one alongside it. And then a very quick summary and decision tree. If you were having faults on site led from pipe sizes, which you think, you may need to go and investigate. Has it worked before? If it has, it's probably not pipe sizing related. If it's something recent, it's probably not pipe sizing related. If it hasn't ever worked correctly, could well be pipes. So carry out your usual checks on site, rule out any typical faults, and then is it present across the entire system? If yes, check between the first evaporator and compressors. And if not, isolate it to that individual section and check there. So that is a whistle-stop tour on some pipe sizing for oil protection. We'll go slightly more in depth on some pipe sizing tomorrow as well. But thank you for joining us on that one. I think Trevor's got a little bit more to add to this. I'll just flick on because ideally,
it's so important. It's so important to understand design. And over the 3 12-week design courses we've done, because my background is not in design, but after working with you and Nabil and with all the students that came through the program, we had over 20 people from 8 different countries so far, finished a 12-week design course. Diving into this and seeing the different options and doing those tasks where they're actually designing it with Cool Selector 2 and then going into micropipe and seeing how much quicker they can do a design, saving half the time. And if we had some people, designers from the course, win jobs because they went and used the micropipe software. And like in week 3 of the 12-week course, this is what we dive into deep on, is into pipe sizing. What is so key, because this can win you a job or lose you a job if you don't design right. And then it can put a bad name for you if you make some bad mistakes where you have to go and redesign a whole thing or redesign a whole section. So this is so important on doing this. If you have the compressors above or below, the evaporator above or below, it's so important to understand how to design for these different systems. So hopefully that you took a few things away from this, because this is just touching the surface. And Chris is an expert. He designed hundreds and hundreds of transcritical CO2 systems, and piping is his game. Like, this guy knows what he's talking about. So if you're interested in a 12-week design, DM me, email me at trevor@refrigerationmentor.com. Say you want to get into this 12-week program, because it has been a game changer for so many people. Here's just a quick snapshot on it. But we want to help you get to your next level. And this is it. Learning about CO2 design. CO2 is going to continue to grow And I can see it here. I have more and more people joining our program saying, like, I'm seeing it more. My customers asking for it. I need to be prepared to design it. We have end users coming into making sure that they can verify what the engineers and the manufacturers are saying, because they want to go, like, they're telling me two different things. And this is why coming into a program that's agnostic, who really wants to help you understand designing CO2 systems. So excited to see some of you there. So remember, reach out. If you have questions, DM me on LinkedIn, email me at trevorrefrigerationmentor.com. And Chris, thank you so much for sharing these quick tips, because these 1 or 2 tips can really change the way you design systems. Any final thoughts, Chris?
No, thank you everyone to join us who various places online. It's good to have some company, and see you all tomorrow.
Yeah, I'm looking forward, because that's where we're going to dive in even deeper on piping design. Chris, thank you so much. And as always, let's get a conversation going. See you, everyone.